Hello everyone. My name is Maliha. Sorry for not being at the campus today. I'm doing this from work. So yeah, I am a recent graduate from the University of Alberta. I did my master's with Osmar Arzayan. And essentially, I worked on natural language processing and machine learning. So today I'll be talking about some of the research work that I've done. The title for today's talk is Exploring Dialog Act Classification in Open Domain Conversational Agents and the Applicability of Data Augmentation. So yeah, it's a big title, but I'm still working on trying to make it more concise. Essentially, I'll be talking about two things in this talk. So the first one is understanding what Dialog Act is and why we need to do some Dialog Act classification when it comes to building better conversational agents, especially when we're talking about conversational agents in an open domain setting. And the second thing that I'll be touching upon is how we can improve model performance or classifier performance with the help of data augmentation. Essentially, one of the biggest problem in machine learning is that a lot of the times we need a lot of labeled data, and finding that can be difficult. So in our research, we explored a bit about how we can tackle that by artificially generating new data. So now that you have a context, let's jump right in. So we're human beings, we love to converse with each other, we're social creatures, and we love to have conversations. Now, one of the building blocks of having a successful conversation is essentially understanding what the other person is talking about. So we need to understand what type of intention the other person is expressing before we can respond to the conversation and have a more successful conversation. So what I mean by that is that if someone is asking us a question, the other person would expect some sort of response from the other person. Again, if someone is giving us an order, the other person would expect us to either acknowledge that order or refuse to do it in some ways. And finally, if someone is declaring something or stating something, they would want us to carry out the conversation by either asking a follow-up question or by saying something that is related to the conversation that we're already having. So all of the things that I mentioned just now, whether it's a question, an order, or a declaration, all of these are what we call dialogue acts. So dialogue acts are essentially functions that we play in a conversation. And in order to have people respond better, we need to learn how to identify these things early on. Now, as human beings, it's very easy for us to identify these dialogue acts. We don't have to think so much. But when it comes to building chatbots, we need to teach them how to understand these type of dialogue acts so that they can respond better to the user needs. For example, if I have a chatbot and if a user is talking to that conversational agent, on the right here, you can see that the user is greeting the chatbot, asking something like, hey, how are you? So when a user is greeting the chatbot, we don't want the conversational agent to essentially look into a knowledge base to retrieve some sort of answer, because a greeting is something very generic. So it can just respond with a preset number of responses to the user and save a lot of time. Similarly, if the user is asking a question, the chatbot in that case would have to look into the knowledge base to retrieve a factual answer. And finally, if there is an order that has been detected from the user, the conversational agent would have to then look into its settings and see whether that order is something it can execute. If so, it will try to execute it. If it is not within its realm, it will say something like, sorry, I cannot execute that. So understanding these dialogue acts is essential for having more successful conversational agents, which can better understand the users. So now let's jump right into the problem that we're trying to solve in our research. So essentially, our team is working on two types of chatbots. So the first one is Anna, or an automated nursing agent. And what Anna does is that it essentially helps relieve loneliness from senior citizens. So other than just helping senior citizens to set an alarm or set a reminder, it also tries to have personalized conversation with the seniors so that they can feel like they are connecting with someone in a way. And another chatbot that we're working on is Mira, which is the mental health virtual assistant. And essentially what Mira does is that it will try to give you resources to manage your mental health, either through giving you a list of therapists that are nearby, a list of the clinics that you can go to, or even give you some resources like how to manage stress or how to manage PTSD, things like that. There is also another module in Mira called Chatty Mira. And essentially what it does is that it will try to have a conversation with the user, especially if they are venting, and almost try to act like a friend who is listening and trying to letting the user be comfortable with them venting to Mira, essentially. So when it comes to having conversational agents like this in two different types of domain, we want to build a Dialog Act classifier for both, which is applicable for both the chatbots. And we want to make sure that it can essentially identify what type of dialogue acts the user is performing. So that way we would be able to give a better response in terms of conversations. So over here, you can see that our ultimate goal is to build a dialogue act or DA classifier. So if a user is saying, show me resources to manage stress, that classifier can classify that as an order. So as we know that when it comes to building any sort of classifiers, we need two types of things. So the first one is we need to have a preset classes that we actually want to identify. So we need to first decide upon how many dialogue acts we actually want to consider and how many are applicable for our conversational agents. So that's step one. And the second step is essentially then building a high quality data set that has enough examples for each of those classes that we have identified. So at the end of the day, we can classify this problem as a multi-class text classification problem because we will be classifying each of the text of the user into one of the classes that we decide upon. So now that we have an understanding of the problem, let's look into what our initial approach was. So initially, we looked into the paper by Kevin Quinn, and Kevin Quinn was actually working in our research team way back in 2015, 2016. So he published a paper called Identifying Questions and Requests in Conversations. And what he did was essentially he tried to detect three types of dialogue acts, which are very general and can be used by any conversational agent. And these are three classes that are general enough that any statement from the user could be classified into one of these three classes. So the first one was whether a sentence is imperative. So for imperative sentences, he looked into a lot of databases that have a lot of orders or advice or suggestions and things like that. The second was interrogative. So this involves any types of questions that a user might ask. And to get examples for each of the interrogative classes, what he did is he did a lot of parsing from different websites to get a bunch of questions. And finally, the last one was the declarative, which is essentially statements from the user. And to get different types of statements, he looked into websites like uselessfacts.net, which has a lot of statements. However, in the end, he was only able to get around 1,200 examples in total for these three classes, which is not a lot. However, one thing to note here is when he made the database, he made sure that the none of the sentences had any punctuation mark, because a lot of the times when users are conversing with the chatbot, they tend not to use punctuation marks. So he wanted to make sure that the database or the data set that he had was reflective of that. The second thing the second drawback with his research was that there was a lot of mislabeled example. So although not only was the data set small with only 1,200 examples, there was around 19% mislabeled examples. And one of the reasons was because he was using a lot of parsing rules, and some of them were mislabeling like statements as questions or questions and imperatives and things like that. However, in the end, he used a classical machine learning model. He used an SVM classifier, and he was able to get around an accuracy rate of 82%, which is not that high. So we wanted to build upon his work and try a few different things. So the first one being creating a larger data set, because 1,200 examples does not seem enough, especially if we want to work on a deep learning model. So initially we thought of artificially creating new data from the already available data set that we have. So using some sort of data augmentation technique. However, given that the data set was already very noisy, we decided not to look into that for now, but we will revisit this topic a bit later. Secondly, we wanted to build a much cleaner data set, so not only a larger one, but one that has less mislabeled sentences. And finally, we wanted to use some more modern classifiers, so some deep learning models to see whether we can improve the model performance instead of just using the SVM classifier, but we still wanted to use it as a baseline for our new model. So here are some of our contribution. The first one is the size of the data set. So we were able to gather or create a data set that was around 38 times bigger than the original data set that Kevin Quinn had started out with. So in our case, we looked at a few different techniques at a few different databases. So the first one being imperative. So for imperative, we looked into data sources that would have a lot of orders or a lot of orders and commands and things like that. So we looked into Reddit, Twitter, a lot of movie and TV show subtitles because they tend to have a lot of advice and orders and things like that. And we also looked into data sets that have a lot of instructions or how-to data sets, essentially. Secondly, for interrogative, we looked into question answering data sets, which already have a lot of preset questions that we could use. And so we already know that the data that we're getting has the right label and is not really mislabeled because we are specifically looking into databases that have the same structure of sentences that we want. And finally, for declarative, we looked into a lot of news articles or product reviews and movie reviews and things like that. So over here, something to mention is that for imperative specifically, we looked into two different types of rules, and we did that through a lot of literature reviews that we had done. And this is the two rules that we had used for the extraction of those type of sentences. Now, second thing that we wanted to do was trying to build a data set that was also a lot cleaner than Kevin Quinn's. And we did a lot of sampling, so manual investigation. So what we did is that the data set that we had, we would take around 100 examples from each of the three labels, and we had around 5 annotators. We gave them those examples to see whether or not that sentence belongs to that particular label. And we repeated this experiment around 20 times. And in the end, we were able to conclude that our data set only had 9% mislabeled sentences. And so it was 10% cleaner than Kevin Quinn's data that he had originally built. So now that we have the bigger data set, a cleaner data set, the final thing to do is to run the experiment. So what we did was, again, as I mentioned before, we wanted to use the SVM classifier as a baseline. And for that in particular, we use linear SVC because it's faster to train, has less parameters to optimize. And obviously, when we're working with text data, we want to do some sort of vectorization before feeding it to the model. And for this, we first removed all the punctuations from the sentence, put it all in lowercase, and then did some count vectorization and TF-IDF transformation to then feed it to the SVM classifier. And another thing, as I mentioned before, we want to build a model, or we want to use a model that is much more modern. So a deep learning model. In this case, we decided to go with BERT because BERT is it's one of the most reliable solutions for natural language processing tasks, especially for text classification, and it has achieved state-of-the-art result in a lot of text classification tests. Now, BERT essentially has two types of paradigm, as we know. The first one is pre-training. So during pre-training, BERT has an understanding of how English language works. And the second is the fine-tuning phase, which we will be doing. So essentially, we will be training BERT on our newly created data set to see how it can perform when it comes to identifying sentences into one of 3 classes. And for the setting of the model itself, we went for the configuration that already works well with BERT in terms of text classification tasks. Now, just to give a quick refresher on how BERT works, as I mentioned before, it has two types of paradigms. So in case of pre-training, it does two different types of things when it comes to understanding the context of the language or understanding the English language better. So the first one is masked language modeling, which essentially means that BERT is given a sentence with some of the words that are masked, and then BERT is asked to predict the words that has been masked in order to learn the language better. And another thing that happens simultaneously is next sentence prediction. So in this case, BERT is given two types of sentences, and it has to identify whether or not one of the sentence entails the other or follows the other. If it does, it will output 1. If it doesn't, it's 0. So that's the pre-training phase. As for the fine-tuning phase, the reason why it's easier and much faster to train BERT is because it has already been pre-trained. It has already a better understanding of the language. So during fine-tuning, all we have to do is add a new output layer, which BERT will learn from scratch. However, the weights that we had already updated in the encoder will just be fine-tuned, and so the training time will reduce significantly. As for the experiment that we actually performed, it was simple. We had the data set, we split it into train and test data, and then we trained the models on the training data, tested them on the test data set. And finally, this is the result that we achieved. So in case of the SVM classifier in our data set, which was 38 times bigger than Kevin Quinn's, our accuracy had a 12% increase. So it now, from 82, it's now 94% accuracy rate. And in terms of the BERT model that we had used, the accuracy is even higher. We have a 98% accuracy rate, which is a 16% increase than the original one that we had started off with. But given that we have worked with a classifier which can detect 3 types of dialogue acts, we thought that that was enough. But upon further research, we found out that that really isn't the case, and there are a lot of issues that comes with using just 3 dialogue acts, as I mentioned before. So let's talk about some of the issues that we found out. So the first one is how 3 dialogue acts are not enough when it comes to capturing the nuanced way that human beings actually talk to each other or talk to chatbots. For example, the first one you see here, like, hey, how are you? Like, this is a question. However, this is a greeting, and a greeting should not be treated the same way a factual question is treated. So this is something we need to be aware of. And the second example you see here is that this is not what I asked for. So yes, this is a declarative sentence. However, this is also a feedback that the user is giving to the chatbot. So the conversational agent needs to learn that it is being given a feedback so that it can better improve its performance in the future. So one of the tasks that we need to rethink is understanding that 3 dialogue acts isn't enough, and that we might need to add more dialogue acts if we want to capture better what the user is asking from the chatbot. So yes, 3 dialogue acts are general, but they're not granular enough to capture all those types of nuances that a nuanced conversation a user might have with the chatbot. So the second problem that we faced or understood we had in our data set was that a lot of the examples we used to build our data set was not really reflective of how users actually converse with chatbots. For example, for declarative sentences, we took a lot of examples from like news data and wiki articles and things like that. And yeah, like our user would not be saying who the residents of Kansas are called or where Obama was born to the chatbot, right? It will probably say something like, hey, I'm feeling down today, or hey, I just grabbed dinner with my friends, or something like that. So we want to use examples that our users are more likely to utter so that our classifier has a better understanding when it comes to classifying one of the user examples. So we need to do 2 things or address 2 more things in our research so far. To do that, we essentially looked into the existing literature on Dialog Acts. So these are some of the domains over here, as you can see, that we explored. The first one, we looked into a few of the popular Dialog Act data sets that are available, one of which is the Switch Data Dialog Act tag set, which essentially looked into telephone conversation between two or more people and then tried to identify the dialogue acts that they were expressing while having conversations with each other. So they ended up finding around 43 different dialogue acts to classify each of the user utterances. So they had something like statement that can be opinion or non-opinion based. They had questions that can be open or WH or rhetorical or yes, no, and things like that. But given that they had used 43 different dialogue acts, there were a lot of the dialogue acts that are redundant, seemed unnecessary, or were too specific to the domain that they were working on. So something along the lines of nonverbal, hedge, or conventional closing. Now, as you can see here, that there are other domains people have worked on in terms of detecting dialogue acts, one of them being building emotional and social conversational agents, in which case they had dialogue acts like greeting, request, encouraging, sympathizing. For education or professional purposes as well, they looked into other dialogue acts they can use to understand user intents, for email and online meetings, and also for social websites like Twitter and Stack Exchange. However, if you look closely, you will see that there are a few dialogue acts that appear more than one times in a lot of the domains. So if we want to build a open domain conversational agents, we should be including dialogue acts that are occurring frequently in different types of domains. So these are some of the steps that we ended up doing to narrow down our dialogue acts. The first one is we identified the common dialogue acts. So we identified the dialogue acts that were common in different types of domains. And the second thing we did is actually investigate how our users are talking to Mira and Anna. So we investigated exactly what are they asking for, what type of functions are they performing through their utterances, and things like that. And finally, we had an iterative discussion with our cross-functional team, which involved people from the psychology department and health science. And then with them, we discussed what type of dialogue acts we should be considering for a conversational agent that is in an open domain setting. So in the end, we were able to narrow it down to 8 dialogue acts. So we expanded from 3 to now 8 so that we can better handle user utterances. So essentially what we did here, as you can see, the first one being informative, and these can be questions that are either yes or no or factual, because the chatbot would respond differently if the question is yes, no versus factual. The second thing we have is directive, and it can be either a direct order, in which case the chatbot will immediately try to resolve that order or execute that order. And the other one is indirect order. So something along the lines of, I need help with managing stress, or can you read me a book? So some sort of request. In this case, the chatbot might not be sure of whether or not this is exactly what the user is asking for. So some sort of clarification before executing that order is something the chatbot might have to do in case of indirect orders. Next, we have statements or declarative sentences in terms of capturing when the user is just venting or trying to have a conversation with the chatbot. Then we have greetings, which can be like, hello, how are you, or goodbye, and something like that. We have feedback that the user might give, and it can be either negative or positive. And finally, if the user had said something that they regret and they want to apologize to the chatbot, there's also another thing called apology. So as you can see here, that we expanded the first 2 classes, and then we added 3 extra classes, and now we have a total of 8 dialogue acts that we actually want to classify instead of 3, because these can better capture the different types of ways user can converse with the chatbot. As for the data set that we now built for these 8 classes, this time for informative, again, we looked into some of the question answering data sets that are available online, but we also looked into a lot of mental health FAQ forums so that we can get questions that our users are more likely to utter. Second, for the directives, we for both direct and indirect orders, we looked into the task completion datasets, which have different types of orders that a user is giving for a chatbot to perform. Next, for statements, instead of going to the Wikipedia articles or news articles, this time we actually wanted the statements to be representative of user utterance in the real world. And so we looked into a lot of mental health forums like Council Chat, where a lot of people will anonymously post about the mental health related problems that they're facing, and they want to ask some sort of advice from the therapists that are available online. So we used a lot of our data from that website. And then we also included some reviews, product reviews and movie reviews and things like that. And finally, for feedback, greeting, and apology, we ended up using some of the examples from different English learning websites that are available. So in the end, we were able to get a total of 24,000 examples. And as you can see here, the first 5 classes that we have are majority classes, and the last 3 are the minority classes. And we couldn't find as many examples for these because they're a bit more generalized. Now, again, we wanted to repeat the same experiment with our baseline SVM and the BERT model to see how it performs in terms of identifying 8 different types of dialogue acts. And yeah, over here, you can see that the SVM model was able to get an accuracy rate of 96%, which is not bad at all. But yeah, again, as expected, the BERT model was able to get a 99% accuracy, which is a 3% increase in the baseline model in terms of identifying the 8 different dialogue acts. Over here, we have a confusion matrix where you can see the true labels on the vertical lines and the predicted labels on the horizontal lines. And so the more yellow one of the blocks is, the better is the performance. So yeah, in case of SVM, as you can see that it struggles a bit when it comes to understanding greetings and as well as feedback. And this might be because these are minority classes, and so it doesn't have enough examples to learn the structure of these types of sentences. In case of BERT, you can see that for most of the classes, it has around 99% accuracy rate, which is great. But we see that, yes, the BERT model performs well on the data set that we created, but we also want to check whether or not our model is actually robust. So what is model robustness? Well, essentially, model robustness means to see the performance of the model when it is being tested on a data set with completely different distribution, which was never used, the sources of which was never used to train the model itself. And ideally, we don't want the performance to deviate that much, but deviation is kind of expected when we're trying to check the model robustness. So to check the robustness of our model, we needed a completely new data set with different types of distribution and different sources entirely. And we will be referring to this data set as generalized data set. And we decided to use the dialog sum data set to build this new data set to essentially test out the model robustness. So we ended up selecting around 227 random examples from the dialog sum data source, and then we manually labeled them into one of the 8 dialogue acts that we have. And here's the distribution. As you can see, we have 8 apology and then 47 statements and things like that. So over here, you can see that when we tested our model on the test data, we tested the baseline model on the test data, it had 96% accuracy. However, when we tested it on the generalized data that we collected with different distribution, the model performance dropped significantly. It dropped by 10%, and now we have an accuracy rate of around 86%, which is not great at all. So from this, we can conclude that maybe SVM model is not really as robust as we thought it might be. However, in case of our proposed BERT model, we see that in the test data, it had a 99% accuracy rate. In the generalized data, however, the model performance did drop, but it's not that significant. The drop was only 3%. And so we have an accuracy rate, which is still 96%, which is still very high and in the 90th percentile. And so we can conclude that our proposed BERT-based model is not only high performing, but is also very robust when it is tested on completely different data set with completely different distributions. And over here, again, we have the confusion matrix where we can see that the SVM model suffers a bit on the direct orders and the identification of yes/no questions. However, in case of our BERT-based model, it has more or less consistent performance for each of the classes. We also tried to do some error analysis and looked into some of the sentences that were being mislabeled. In case of SVM, we see that a lot of direct orders were being predicted as either statements or yes or no questions, which is not great. And we think the reason for this might be because a lot of the direct order examples we had in the data set were very simple, like turn on the lights or please turn on the music or something like that. And so the SVM model, when it got some more complex direct orders, it wasn't able to understand them as properly. Same goes for the yes or no question. Most of the yes or no question were a bit formal for our data set, but over here, these are a bit more natural sounding sentences. So the SVM model had some trouble understanding them. As for the BERT model, we can see here that sometimes apology and greeting are mislabeled as statement, which kind of makes sense if you see the sentences here, which can be classified as a statement in a way. And for yes or no questions, you can see here things like, have you turned on the air conditioner? Can I exchange it? These are some things that can be also labeled as indirect order. So when there is ambiguity in the Dialog Act itself, sometimes BERT also has a hard time figuring out or labeling them properly. So far we have talked about how we can select Dialog Acts that are that are not only general but granular enough to understand user intents. Secondly, we talked about how we had an annotated data set that is of high quality and has multi-domain examples. And finally, we talked about how we used a BERT-based DA classifier that is not only high performing, but is also robust. But if we take a pause here, we will see that there's a pattern when it comes to using machine learning models. When we're using newer sets of Dialog Acts, we are having to create a newer data set. And we have seen that when we use a larger data set, the model performance improves even more. But getting labeled data can be very difficult because it is very time consuming and it takes a lot of time and effort to do that. So over here, what we wanted to look at is there a way to tackle a problem that most machine learning models have through data augmentation? So what data augmentation essentially means is techniques that can be used to artificially generate new data by transforming the original data that we have. So what do I mean by that? Well, essentially, suppose I want to build a model that can detect my dog Poco from the rest of the dogs. And to do that, I would need to essentially take different pictures of my dog from different angles, and that can be very time consuming, right? Or I could try doing something like that. So I could try to flip the picture that I have, rotate it, crop it, or change the color, and essentially have 4 different pictures of my dog from just one picture I originally had. So if I had 10 pictures of my dog, I could again repeat this experiment, and now I would have like 50 images of my dog, and I can train a model this way. And if I include diversity into the database in this way, that model will also be more diverse and more robust. So this is what augmentation means in general, but how do we do data augmentation on text? Because we know that text or natural language is a lot more discrete and nuanced, and it is very complex because it has a lot of syntactic and semantic structure that we need to be aware of when we are actually doing data augmentation. So if I have a sentence like this, I can't just rotate it or flip it to get a new sentence because it no longer makes any sense, right? But we have looked into a lot of augmentation techniques that are being used in natural language processing these days. And we actually have a taxonomy that we used to understand the different types of augmentation techniques that we can use. So suppose I have a question like this, and I can use different types of categorical augmentation techniques to essentially create new data. The first one being EDA, or easy data augmentation, which essentially means which can be contextual or random. So in case of contextual, we can either take a word from a sentence and then replace it with its synonym, antonym, or things like that. Or I could also do it more randomly, selecting a word and swapping with it with another word in the sentence and generating a new sentence that way. The second thing I can do is paraphrasing, which essentially means that the original sentence and the new sentence will have the same meaning, but in a slightly different way. So there are 3 ways I can do that. The first one is machine translation. So I can take a sentence in English, translate it to German, and then translate it back to English. And because of the difference in translation, I'll have a new sentence that is still reflective of the original meaning, but is slightly different from the original sentence. I can also do control generation or rule-based techniques where I essentially change an active voice to a passive voice and generate a new sentence. And the final category is the compositional generation, in which case we can use, the new sentence does not necessarily have to have the same meaning as the original sentence, but it still has to have the same label. So over here, I have a new question, but it is still a question nonetheless. So I can do that using language model where I mask some of the words and then ask BERT to predict the word, and thus prediction can generate a new sentence. I can also ask GPT to complete a sentence for me through prompting, and I'll have a new sentence. I can also do that using generative models, interpolation, where I add noise into the vector space, or I can do structural transformation where I essentially change the parse tree, like swapping the object with the subject. However, we need to keep in mind that when we are using techniques like this, the newly generated data might not be label preserving in a lot of the cases. So if we're talking about sentiment analysis task, if I have a positive sentence, like I'm going to eat my favorite meal today, and if I do some prompting with GPT and it ends up generating a sentence that is completely negative, adding sentences like this to your data set will add a lot of noise because this sentence is no longer positive, right? So instead of increasing the model performance, these type of augmentation techniques can decrease them. So we need to be careful of the types of augmentation techniques we use depending on the task that we perform. Now coming back to our problem, which was Dialog Act classification, and how can we use augmentation techniques for this? Well, as I mentioned before, that we were able to get a data set which had almost 24,000 examples, which is a lot. But what if we weren't able to get that big of a data set? What if we had a less amount of time and we only had a small data set to work with? Could we still make a good high performing model with a small data set, but then do augmentation techniques instead to increase the size of the data, add diversity so that the model is more robust? So to answer those questions and to see whether model performance can be improved with augmentation techniques without the need to scrape websites to get loads and loads of labeled data, we wanted to simulate a low data regime, which means that we wanted to randomly sample around 10 examples from our big data set for each of the label, or take around 100 examples for each of the data Dialog Acts from our data set, and have a small subset of our original data. Then we want to apply some sort of augmentation techniques to artificially generate new data from the subset that we already have. And finally, as you can see here, that once we add those artificially generated data to the subset of our original data, we will call this augmented training data. We will train our BERT-based model on the augmented data and test it on the original test data to see whether the model performance is still around the 90th percentile. So before we jump into the experiments, let's take a look at some of the examples that we were able to generate through different augmentation techniques. So here I have the original sentence, like I feel really down all the time. And we use different types of augmentation techniques like random delete, where you randomly delete a word from the sentence, random insertion, where you randomly insert a synonym of one of the words here. We do random swap, where you swap 2 different words in a sentence. Synonym replacement, where you replace a word with its synonym. EDA essentially takes one of the 4 above mentioned techniques and tries to generate a new sentence from those. Back translation essentially here translates a sentence from English to German and back to English to get a new sentence. Masking and prompting I've already mentioned before. So let's jump into the augmentation experimentations. So over here, you can see that we first decided to take only 80 examples from our 24,000 examples of the original data set that we had. Then we applied different types of augmentation techniques on it to almost double the size of the data set from 80 to 160 almost. And then if you see at the model performance here, we trained the BERT model on only 80 examples, and it was able to get an accuracy rate of 76%, which is much lesser than the 99% we had originally gotten, right? However, if we train the model on the artificially generated augmented data, we see that the model performance increases by as high as 8%, and model performance jumps to 84% accuracy rate. So if we just have 80 examples and we use augmentation techniques like synonym replacement, the model performance can improve to 84% accuracy, which is amazing. For the second setting, again, we tried to see, we only used 800 examples from the 24,000 examples that we had, and then again, used augmentation technique to double the size of the data. And again, we trained our BERT model. And as you can see that on 800 examples, when the model is trained, the accuracy rate is only 88%. But if you do augmentation techniques and train the model on the augmented data, the model performance can improve as high as 96%, which is very close to the 99% accuracy rate we had gotten when we used 24,000 examples. So augmentation techniques can definitely help when you have data scarcity or when you don't have enough data, but you need to create you need to artificially generate new data to improve model performance. However, there are a few caveats here. For example, in case of back translation, you can see that instead of increasing model performance, the model performance is being decreased here. And the reason for that, again, is that because a lot of the back translation sometimes will change the meaning of the sentence. So a sentence that was originally a yes or no question turned into a statement. And so this instead added noise to the data set. And so the model performance reduced. But all in all, we can conclude that DA classifier can improve performance in the face of data scarcity using augmentation techniques. And the best performing ones here were synonym replacement and prompting, whereas the worst performing ones were back translation. Another thing I want to quickly touch upon is another goal of ours. So not only did we want our conversational agents to be multi-domain, but we also wanted them to be multilingual. So one of the languages that we're currently working on is French, because we also have a lot of users that speak that language. So we want our chatbot to also understand those users. So for this, we again wanted to build a dialogue act classifier that could classify those 8 dialogue acts, but this time from French language or French sentences. So we already have an English training data, right? So all we have to do is now translate it to French. But the problem here is that the automatic translation that we tried with Google Translation API was flipping a lot of the original labels into something else. And so it was no longer label preserving and the sentences lost their meaning. So instead, we opted for manual translation. So we had 2 translators and we gave them 40 examples for each label. And in the end, we were able to get a French data set with 234 training examples and then 150 test examples in French with those 8 dialogue acts. And this time we not only wanted to use BERT, but also we wanted to use a multilingual BERT because that has a better understanding of the French language. And we believe that that is something that because of that reason, the model would have a better performance. And yeah, given that the data set was small, we decided to increase the number of epochs so that it can better understand the pattern of the text. In case of BERT, we see that when we have 10 epochs, it's able to get a 68% accuracy when trained on only 234 examples in French. However, in case of multi-BERT, because it has an understanding of the French language, it was able to get an accuracy rate of 80%, which is great. Again, given that we only have a small data set this time, we thought can we use data augmentation techniques here in a different language, increase the size of the data, and then see whether model performance can be improved or not. And that is exactly what we tried to do here. As you can see, we have an original sentence in French over here, and then we have different types of augmentation techniques. We did a few tweaks here. We, instead of using a French English dictionary, we looked into a French dictionary to get the synonyms. And then for back translation, we did from French to English and back to French. For masking and prompting, we used models that are trained on the French language so that they have better predictability when it comes to French sentences. And so in terms of the results, as you can see here, we originally started with only 234 French sentences, and then we doubled that data set by doing different types of augmentation techniques here. And then on BERT, as I mentioned before, it only had 68% accuracy rate with only 234 examples. But if we train the model on the augmented data, we see that the model performance can be improved to as high as 72% accuracy. So a 6% jump in the accuracy rate, which is great. And for the multilingual BERT, again, the random insert worked best for the French language. And from 80% accuracy, we were able to jump to 84%, which is amazing. And yeah, in the end, we can again conclude that we can increase Dialog Act classifier performance, especially when we are in a data scarcity by using augmentation techniques. In this case, random insert did the best, and the worst was random delete. Last but not the least, we also took a look at augmentation techniques and how it can be used for not just text classification, but also other types of NLP tasks, from text categorization, like using the BBC News, to sentiment analysis of different types of movie reviews from IMDb, to emotion detection on the career dataset. Then we also looked into dialogue slot and dialogue intent detection tasks. And over here, as you can see, that we started off with 10 examples for each label and 100 examples for each label. We repeated these experiments with different augmentation techniques, and we saw that a lot of the times augmentation techniques can improve model performance, and EDA was one of the techniques that worked in most of the cases. And yeah, to summarize what I've talked about so far, we showed how we can come up with a Dialog Act taxonomy that works for an open domain conversational agent. Then I've talked about how we built a data set that is reflective of how users converse and has examples for each of the 8 Dialog Acts and how it has examples from multiple domains. Then I've talked about how we built a BERT-based model on our proposed data set and prove that it is not only high performing, but also is robust. I showed how we can, in case of data scarcity, instead of going for finding out more and more labeled data, we can just start small, have a small data set, use augmentation techniques on the small data set, and still have a model performance that is as high as a model that was trained on large amounts of data. And finally, I also showed how we can use augmentation techniques for not just English, but other languages like French. So yeah, these are some of the papers from our work so far. And I would like to conclude my speech here. Thank you so much for all your time. And I hope I was able to present something that's a bit knowledgeable. But yeah, thank you so much. If you have any questions, feel free to ask.
Okay, I will speak to represent the room here. Russ has a question.
I just use my outdoor voice.
Can you hear Malia?
I think so.
So thank you for an interesting presentation. I'm curious, how well do people do on this test? Would I get 100%? Would I get 95%? Did you try what you did on it?
Would you mind repeating the question, Danielle? It's not as clear.
Russ is wondering how accurately humans do on the testing.
Which one?
for both questions, both the 3-way as well as the 8-way question?
Both.
How well humans do? Yeah, that's a good question, because in case of understanding the Dialog Acts, when we were doing the manual inspection, different people had different opinions. Like some would say, okay, this is not a question. I would rather say that this is an imperative sentence instead. So a lot of our discussion went into actually defining what we mean by each of the classes themselves. And I think that helped us to then actually move forward with that. So when we are working with Dialog Acts in general, a good idea would be to actually define what each of the classes mean for your model, so that it's easier for everyone else to understand and for the model to understand.
Did you compute kappa scores?
Did you compute kappa scores?
No, we did not do that. Like that is, I think, one of the limitations. In case of that manual inspection, it wasn't as calculated. Yeah.
One second. Malia, do you mind just speaking? I'm just trying to use a microphone here for the room.
Okay.
Malia, do you want to repeat?
Am I audible?
Yeah, you are now. I'm just trying to get the microphone for the room to work as a microphone in the room so that it's not through my computer.
All right.
Can you hear me?
Not as clearly.
What about this?
We can just use louder voices. If I unmute, does that help?
Can you hear us?
Yeah, I think I can hear now.
Okay, so if I take this with me, does it take the sound? Yes. May I ask me questions? Yeah.
Well, we know for next step.
Okay.
Can you hear me? Hear me? Do I have to push the button or anything?
You shouldn't.
1, 2, 3.
Can you hear Russ?
Yeah.
Okay. Yeah, you shouldn't have to push anything.
So what's the penalty for being wrong?
Now I can't hear. It's very muffled.
I can go back to my outdoor voice if you're out. 1, 2, 3. Hear me now?
Yeah.
What is a penalty for being wrong? If you mislabel an utterance and you claim it's an apology rather than a narrative, what happens next? How bad is it? Are they all uniformly bad?
What is the penalty if something is detected as mislabeled?
Yes.
Okay. Yeah, that's a good question. In our case, what we wanted to do with the BERT model specifically is try, we made sure that all of because we had a few classes that were minority classes, we made sure that equal importance was given to each of them when they were being predicted. I think the good thing about BERT is that some of the differences that we have in case of like question versus order versus statements, like those are more, we need to understand, those need to be classified better. And some of the things like feedback versus statement, that is not something that is as important to distinct between the two. And in case of the performance of our BERT model, we saw that that wasn't the case, like that was the case. So it was for this classes that actually mattered, it was able to identify them distinctively.